Now,
Yes, yeah. Yes, sir.
the dish you can see here.
Yes, yeah. I'm seeing like this.
See, if you compare these two, one is dish, the other one is parabolic trough. Okay. So here, what happens is now this aperture, this entire aperture, whatever solar radiation fall on that will be reflected to the receiver here, isn't it? Yes, so now if you write energy balance at the receiver here, the heat loss, the heat input minus heat loss is the net heat output. So the heat loss dependent on, basic heat transfer equations. Either it depends on the heat transfer coefficient or temperature difference or the area. Yes. Q is equal to HA delta T. HA delta T. Or H can be either convective or radiative, any heat transfer coefficient. So then how, because delta T is higher, isn't it? The delta T, because temperature of ambient we don't have anything, any control, but we can raise the temperature to higher, the T1 minus T2. So T1 we can increase very high. Yes. But when we increase the T high, it will lose to the atmosphere through either area or heat transfer coefficient. Okay. So if we reduce the area, we can reduce the heat losses, or we can minimize the heat transfer coefficient also, we can reduce it. Yes, sir. Yes. So therefore, these are the challenges. So area, how do we reduce? You make it a smaller receiver, so that you will have a better efficiency. Yes. And how do you maintain smaller receiver? Because you make it an accurate parabola and make it a very sharp focus so that you can do it. And the heat loss coefficient, mainly it's due to convection by air, convection by wind and other things. So you try to avoid the wind by having another envelope over that. Okay. Now I hope you understood. Yes, sir. Vacuum also we can maintain to avoid. What we can maintain? Vacuum based receiver also. Yes, yes. Correct. So we reduce we evacuate it. Evacuation, yes. Also, the bottom one is evacuated so that your convection losses are suppressed. Yes, sir. Thank you, sir. Thank you. Dear participants, any else? Shall we switch to second presentation? Yeah. Yes, sir. We can go start the second lecture. So now you can see the second presentation? Yes, sir. Came, sir. It's okay. Presentation. Slides, you can see that, no? Yes, sir. Thermal energy storage. Yes, sir. Slide came. So this is thermal energy storage in concentrating solar power for improvement of reliability. Yeah. Okay. So in the previous case, we have previous talk, we discussed more of conversion systems, energy conversion systems. But these solar systems, they work only during daytime, and nighttime you don't have a solar energy, so therefore we don't get any output. But our usage, we use nighttime also, no? The energy, electrical energy or any energy we use also nighttime. But then how do you make the solar energy available nighttime? Not only nighttime, what happens is during rainy season, now everywhere in India is experiencing rains. So during rainy season also, we don't have, we may not have solar energy. Then how do we make this solar energy in rainy season also? So that is possible only. See, reliability means we have to dependent on only solar. 100% means that system should be able to supply the energy 24 hours and 365 days. That is only possible with the thermal energy storage. The energy storage plays a major role in reliability of power plants. So we will discuss here reliability of power plant, what are the different thermal energy storage systems and so on. We have seen in the previous case, in the beginning, my introduction, I have mentioned that solar energy can be converted directly into electricity in two ways. One is photovoltaics. The photovoltaic means it converts solar energy into electricity and you can connect to the grid. Okay. And this is a grid, either it can be grid connected or even standard. We can use it in houses also. In such case, in order to improve the reliability of this, you can have to go for storage. That is a battery storage, electricity storage, or we can go for any auxiliary system. In contrast to this solar thermal storage collectors, this collectors converts solar energy into heat, and that heat we can supply to the power plant cycles, which produces electricity. You can either connect to grid or standalone. But here we can have some storage in order to improve the reliability. This storage is, in this case, it's a thermal energy storage. If you can store thermal. See, solar energy is available only 8 to 10 hours, but remaining 14 to 16 hours we may need energy. So that 14 to 16 hours we can store in storage and then use it whenever there is no sun. So during night time. That is the concept of thermal energy storage. There are it's important to operate renewable energy grid, because there are flexibility, as I mentioned, not only reliability but also flexibility depending upon the fraction of renewable energy. If there is a 20%, we have a grid generation, consumption, storage facilities, because storage can also be used in different ways. So our focus is storage here, but there is a penetration of renewable energy into this one depends on how they are, what is the flexibility and all. This storage facility plays a major role when we have a surplus energy. Either we can go for pump power or like thermal energy storage or power to gas system. So there are a wide variety of options for flexibility of energy storage. Mainly you can see here the type of intervention and their cost also have given here. What are the different options depending upon the load, whether the storage, you can see which storage you go for, whether it's a chemical storage or fuel storage, or pumped hydro or thermal storage or any other storage we go for. That is an important place. But as we go for different storage, you say the cost will also go up. Generally, if you see, just now I mentioned that for photovoltaics, we may have to go for electrical storage in the chemical form. So therefore, this will become, I think, relatively expensive here. And the best one is a thermal storage. You can see in this, the cost is lower as compared to the other storage systems. So therefore, in my talk, I am going to focus on this thermal energy storage, how it is focused to this concentrating solar power. You can see that it's a concentrating solar power. These four technologies are very important for converting solar energy into heat, but they are available only daytime. But then if you operate this daytime, and you can still produce excess energy and store it and use it in this case. And this I have already mentioned, the medium temperature and high temperature depending upon the technology. So now if you take, for example, this parabolic trough technology, how do we connect to this system? Then I will show you here two concepts which we call thermic oil based, synthetic oil based. Morning, some participants asked about what is the working fluid here. This is a synthetic oil. This is a direct stream generation. What we can do is we take a synthetic oil, heat it up, and then transfer into the steam generator, and this cycle operates on this. This is called thermic based, but we can avoid this by using direct stream generation, where the water can directly go into the collectors and then come back. But this is better heat transfer point of view, but there will be thermal instability, thermal issues are there, two-phase problems and so on. But most extensively used across the world is this thermic fluid based system. The purpose of energy storage. You can see that during the daytime it operates like this, but your load capacity is this much. Then we will produce excess energy. This excess energy which goes to the storage, and then it can be retrieved after the sunshine hours, maybe for example after 7 o'clock, and then use it for this. So this, you can shift the storage into the extended operation. But how much storage you store is very important, whether you store only for 2 hours or you go for 16 hours or you can go for entire cycle, that is an important thing. It's a trade-off between the cost and the operating hours. So here I have taken, for example, only for 2 to 3 hours. Here 9 to 21. I got 2 to 2.5 hours we have taken. So in such case we have to go. If you have more, if you want more energy storage, this storage we need to increase that. Then again cost will go up. Then there are three different energy storage systems. ESS means energy storage. There is a thrust for renewable energy source. Viable outputs are important, and energy buffering is also. If there is a all of a sudden cloud coverage is there, then we need to store it temporarily, which is called buffering. And it's important in the present context because the viability of, and reliability are flexibility are important. So therefore, we have to use new technologies, new devices for that. Storing renewable energy system and integration is very important, and it can be grid connected or non-grid connected. We have to make it cost effective, and we have to look at the capacity, load leveling, and reducing cycle and ancillary services and so on, and distribution with the storage, whether minimum with you have to use minimum infrastructure, minimum losses. We need to use a necessary storage, and also for an integrated one, renewable energy should be it's a value addition to the renewable energy. So there are different energy storages are can be proposed. One is a mechanical energy storage in flywheels, magnetic energy storage in magnets, and thermal energy storage in the form of heat, chemical energy storage either in the battery or thermochemical form. Potential energy is based on the pumped hydro and of course pumped hydro energy. These are the different types of energy storages. If you look at energy storage options here, you can see that where pumped hydro, batteries, metal to their long duration flywheels, and this one lithium ion high power flywheels, and there is a capacity versus this one is there. Capacity of this one. So energy management is very important. We can go for large capacities, thermal energy storages, and so on. That is an important thing. Now, if you look at the energy storage options here, somewhere covering from super capacitor to the flywheels and flow batteries, because we are also working on, and hydrogen storage, molten salt, and this molten salt and hydrogen storage. Molten salt is a thermal energy storage. And what level they are, whether it's I told you 4D approach, research level or 4D approach, research, development, demonstration, deployment, and of course mature technologies also. You have to see that how these are implementable. Then we have to see how this, how do we store solar thermal energy. There are three basic processes. Thermal energy store can be either sensible, latent, or thermochemical heat storage. Here, sensible means heat is added in one phase, and so sensible energy heat can be retrieved and without much phase change. Latent heat is with phase change. Either could be melting or freezing or vaporization or fusion or any process by which we can transfer heat. The other side is a thermochemical, where the chemical heat of reaction or thermochemical heat can be used, maybe either some phase change materials. In terms of this is a latent heat is a physical phase change. This is a chemical phase change. Thermochemical is a chemical phase change. And there is a sensible energy storage. Generally, if you want to find out what the energy stored within the sensible is, we have to say this energy is equal to MCP delta T with the time. So it's you have to integrate with the charging time to recharge final time. That's important. And of course, the temperatures also, what temperature to what temperature you are doing that. That's an important thing. Then if you take a typical thermal power plant with the storage is this. There's a parabolic trough collector, but you can integrate with this hot and two tanks, hot and cold tanks, and they first during the daytime it heats up the hot tank, and during night time it will reverse the flow. So therefore the cycle is also reversed, so that we can be operated in the night time. And if there is additional energy required, we can even go with the auxiliary system. So because this two tank system, because in solar thermal power plants, it operates only 8 hours for the given capacity. But if you want to store energy for 24 hours, then you have to store 16 hours. See, actual operation is 8 hours, but the storage option is 16 hours, almost 2 times the capacity of the plant we need to store. So therefore, having 2 big tanks will have a major challenge because they are very expensive. So if you go for 2-tank thermal energy storage system, it's of course matured, low risk, reliable system, but very costly. It's a very expensive for energy. There are some power plants across the world under Sol and power station and Gamma Solar, also another power plant where they have used large scale power plants here with a 50 megawatt to 20 megawatt capacity with the different temperatures. And of course, there's substantial improvement in that. It's a thermocline, but the problem is 2 tanks is literally 2 tanks. Only 1 tank is ideally in use. So therefore, the cost of these tanks will be high. So if you replace these 2 tanks by a single tank, then it's called a thermocline single tank system. We have been working on energy storage with a single tank. That's called single tank thermal energy storage system. It's a combination of both hot and cold fluid in the same tank, and costly molten salt is replaced by cheaper filler material. So therefore, it's a better option. Now, for example, if you look at schematically, there are 2 tanks. During daytime, what happens is the heat is stored in this hot tank. During night time, the hot stored tank will go back to the cold storage. So in the process, the cycle is operated. So these 2 big tanks will be cost intensive. So therefore, we can eliminate these tanks by a single tank like this, which is called thermocline tank. In the same tank, the thermocline is established, and then it moves from forward to backward and backward to forward. This is an important tank, and we have done extensive analysis on this, and we are also doing a lot of works on this. In fact, again, I'm unable to show some detailed systems. Why? Because there are IPs involved. Some industries are participating, mainly Indian Oil and other big companies are participating. So I am unable to show that, but I'll give you glimpses of this. There are different organic metals, mainly for storage medium, and then inorganic materials like this with a different temperature ranges, with energy densities and heat of fusion and all this. So you can see here, and they can be employed different fluids. So if you connect them into a single tank, here it looks like this. There is a distributor, and then it moves during charging. It moves here, and discharging it moves opposite direction. And there is some expansion vessels, and this one is a power plant cycle. And this is a solar parabolic trough collector field, and it is produced excess energy stored in this tank. And if it moves, you see it's charging moves like this. It's but it's a packed bed thing. It moves like that. So therefore, filler material is very important. We have done thermodynamic, heat transfer analysis for this. This is a mixture of quartz, rocks, and sand here in this, and it's insulated. See, this tank is taken, and it's taken centrally from the left side. The sides are insulated. So we can, when we analyze it, whether we need not have to analyze completely. We can take half of the cycle, half of the tank, and then analyze it, and the rest will be the same. So this is a half of the tank. This is the axis of the tank, and the left side is this mixture of this energy storage, and then there is a insulation of this. And phase-change materials are used here. Here some the PCM 300, PCM, this one highly volumetric energy densities, constant outlet discharge at the temperature. We have there is of course some assumptions here. As I mentioned, that is asymmetric here, and the different packed beds are used with the phase-change material, different materials, energy storage material. This is the tank, and boundary conditions are applied in order to study the analysis. So this is governing equations. I am not going in detail of this. You can, if somebody is really interested in this work, we have already published papers. You can check those papers. And how to validate this model with molten salt temperature versus axial tank distance, and then for different timings with the T initial to T plus 2 hours. And similarly, the charging time with the temperature. This is a distance wise, and this is a charging time wise, and it's completely both the models, the sensible heat as well as latent heat models have been validated, and they are good, reasonable limits are good limits. And the analysis of single-layered packed bed tanks have been done with various things: effect of design parameters, effect of SLPV tank, and that is a thermocline tank, and effect of operating parameters compared to parametric study. We have done general behavior with tank and other things. So we have taken various parameters of the tank and various void fractions and so on. General behavior of tank. This single-layered packed bed thermal energy storage tank is mentioned here. Charging time, discharging, how it behaves charging and discharging with the axial distance of that. And of course, this further analyzed by taking a periodic state initial conditions, how the tank thermocline moves from bottom to top and top to bottom. You see, in discharging mode, it will move up. So this one is moving up here. And you can see that effect of design parameters, how they behave on this, and what is the molten salt thing with the different diameters of the bed and so on. So thickness, filler material sizes, and all those we have seen here and optimized here. So it is varied from 10 mm to 1 centimeter to even 6 centimeter size and so on. And we found that. And effect of operating parameters, mainly velocities of molten salt, how it is influencing that, and discharge efficiency, how it's dropping, and all these are shown here with this thing. And we have also seen operating temperature for different cases also with the different temperatures and with the different initial and boundary conditions with the different characteristics of these. You can see with the different cases how the behavior is behaving here, discharging time and charging times and so on. And because it's very, these are very deeper analysis, I don't know how many of you can really understand, but why I'm giving this, because if you give glimpses, you should be able to, if you want more, those who are interested, more information on this, they can go to our papers, they can check it, and if you have still doubts, you can contact me later by email, no problem. And how this discharge efficiency dependent on the velocities and also power outputs. If we change the power output from 15 megawatt to 35 megawatts, how it behaving? How is it behaving with operating temperatures, with the discharge efficiency? You can see that. At lower temperature, obviously the efficiencies are higher. As we go higher temperature, the efficiency drops. And similarly, the velocity at lower velocities, you will have a higher discharge efficiency, but when the velocity increases, the temperature drops, so the efficiency will also drops. And then multi-layered, if we have used a single layer, but if you go for multi-layer design, if the bed materials are not same, if the different staggered system, then how the thermocline multi-layer will be like this. You can see that charging and discharging characteristics. Instead of one layer of bed, we'll go for 2 layers of beds. But this size, total overall bed size is same here. So this bed size is same, but it behaves differently. The thermocline thickness will differ from single to multiple cline. Thickness means the temperature gradient across the thermocline will be different. So that's an important thing. And there will be temporal variations of outlet temperature with both molten salt temperature versus time, and you can see the behavior of that both for charging and discharging of activities. That's the difference here. For various Prandtl number, it has been carried out, and discharge during is higher with the salts having low Prandtl number and so on. And we can also see comparison of single and multiple layered tanks with a different thing. You can see here axial temperature distribution has been carried out, and considering initial conditions are because initially it's a dotted line, you can see that, and as time progresses, the curves move from the other end, and for the same dimensions of the tank, duration of discharge for multiple layered tank is found to be 5.32 hours, whereas it is 4.19 hours in case of single tank. So even introduction of PCM in 20% of the entire filler material increases about 1 hour in discharge time. That means we are increasing discharge time so that we will have a better operating conditions. And then effect of PCM width. Width is also important. So energy delivery as well as the duration of discharge is increased, and the increase in duration of discharge with PCM with comparatively less because the percentage is less, and more PCM is required for more, of course, more investment, more cost involved in that. So therefore, it's a trade-off. One has to take care of the trade-off between the total energy, sensible energy, and latent energy. How the height of the height of beds and width of the PCM changes here. Tank size also plays a major role, and it's a volumetric energy density is important for the given size. So new volume of tanks and the height is varied, keeping the tank diameter is the same. If you go for higher heights, then your pumping power will be different because it increases. So therefore, we cannot go for taller tanks. If you have a taller tanks, what happens is the thermal stresses are higher, and then structural stability is also very important here. And you see that this is the cycle with the energy storage here with both steam storage and all. This is a mini power plant which is in on our roof of our lab, the CRC lab. You can see both the plant. With respect to these people standing on this, you can see how big they are. It's almost the crane size, which is the back side. You can see there. So here you can see that there is a foundation so exclusively made for this because it is isolated from the building. Otherwise, this is a massive load. This is on 4th story building. This is almost terrace of 4-story building, and you can see that because in IIT we have a lot of vegetation, greenery is there. It's very difficult to find space for ground mount systems. But this is a massive structure. As I mentioned, our approach is 4D approach. So therefore, it's very difficult. This I have shown you in the morning how just before how this one you steam and other power plants with the kg design. This is also school system. Why I have shown again because how storage can be integrated with this system. You see that the storage can be integrated in here. That's why I have repeated that. So with this, we have discussed complete energy storage, how it can be integrated with concentrating solar power. What is the importance of energy storage in thermal concentrating power? I have discussed. I think I hope you understood some deal of material from these two presentations. But I'm very sorry for the morning session because of some technical stack. But of course, it's beyond our scope or beyond our limits. But anyhow, with that experience, it will be good. So I think because I want to spend some more time on questions if we have. And another thing is because I think most of you are a bit hungry, so that's why I have a bit speeden up, a bit fast enough. But nevertheless, we can discuss maybe 5 to 10 minutes if you have any questions. Okay, thank you so much.
Thank you, sir, for discussing various thermal storage methods such as packed bed, phase change material, etc. And you actually 2 lectures are clearly covered about the thermal energy collection, storage, and utilization parts of the solar thermal energy. Thank you, sir, for your topics. And now I request the participants to ask the questions in this topic, these two second topic, thermal energy storage.
But the second talk is there was no disturbance, no? It was perfect.
Yes, very fine, sir, very fine. And today morning, due to some technical problems, we faced that interruptions. Now it is sorted out by our technical staff. Now it is clear. There is no disturbance.
Okay, very good, very good. Yeah, please go ahead if you have any questions and answers.
Sir, what is the way forward for energy storage? Because a lot of renewable energy is focusing by the government of India. So what is the way forward? How will suppose fuel cells and battery, the major challenges area?
Mm.
How will we minimize the risks and opportunities?
So I have already discussed several energy storage options. See, in this, I have not covered one phase change thermochemical energy storage, which is the hydrogen production. The hydrogen is used in fuel cells. You know that very well. But the end-to-end energy conversion, the fuel cell is um, an energy conversion system, but the hydrogen need to be produced. That is the secondary energy carrier. But hydrogen is not a source. It has to be produced from the other uh, feedstocks, mainly other materials. When one of the cheapest material is cheapest feedstock is water. You can split water into hydrogen and oxygen, and that hydrogen can be stored and used for fuel cells. But the if we use for converts, this is called decomposition of hydrogen water. When you decompose, means you split water into hydrogen and oxygen. A large amount of energy is required, and if you use by fossil fuels, again it's a pollution. So it's better to use some solar energy. We are also working on thermal decomposition of water, splitting with different feedstocks. One is the water, other one is methane. Methane is CH4. If you split methane, we'll get carbon and hydrogen. Methane can be found from generated from biogas. See, biogas we produce and then split into hydrogen and oxygen. It's enriching, actually, biogas enrichment. If you enrich with hydrogen, then that hydrogen can be used for fuel cells, or not only fuel cell, but can also be burnt and can be used for long times. Like you produce hydrogen by solar energy in summer and use it in rainy season. That's a extended seasonal storage. And another one is a battery. Battery storages are coming up seriously. There is a lot of potential. Now lithium-ion batteries are there. Now recent phenomenon is a lithium sulfur battery because the energy densities are higher and its cost is very low, because you know that in India, mainly if you look at the present government is focusing on um, mainly this energy sector.
Renewable energy.
Renewable energy, not only renewable energy, but also see, we want to minimize the fuel imports like oil imports. Okay, so the oil imports are mainly major oils are used for mobility. Okay, mobility means our cars. If we replace these diesel and petrol cars by electric mobility, that will be a great. This one now, this present government has a lot of emphasis on e-mobility, electric mobility. So for electric mobility, you need batteries. Now even I've seen at least 2, 3 automobiles. They are mainly cars, passenger cars. They can go for up to 300, 350 range with the this one charging. But the charging stations also have to be renewables. Okay, it's not like a solar plant. If you take a petrol pump type of thing, you can have a charging station where charging is done with a solar plant. So like that, the energy storage plays a major role. You have any doubt, further clarification on this?
No, sir. Thank you. Thank you for your. Sir, can we receive these PPTs? This is very informative sessions. Is it possible?
I have to check with the organizers, but anyhow, it's recorded, no? So that is more than enough for you, isn't it?
Sir, AICT, their website, they are giving the link to the presentations.
That video link they are giving, no?
Yes, sir.
Okay, so that's even you can see all of this. There's no problem. Because nowadays, even we are taking online classes also, a lot of space requirement, because data is too much data actually. Data is very important. Anyhow, we'll see that. Yeah.
Any questions? Krishnara.
Sir,
Yes.
sir, can you
Krishnara.
please tell us the softwares available for the design of CSP systems?
Softwares available for design of CS.
CSP.
P- yes, sir. PTC, LFR, CLFR, and DISH and all.
Uh,
So, which software we can use
so,
to
what are the
design?
software?
Yes,
So,
sir.
in you know that there are, as I mentioned, that in a CSP or solar thermal collectors, as I mentioned, that there are three components. One is receiver, other one is a concentrator, third one is a support structure. So receiver is a thermal element. Okay, that's a heat transfer is involved. So we have to, for designing that, you may need heat transfer related softwares. The second one is a concentrator. The concentrator is an optical element. Optical means that the ray, solar rays come and reflect back to that. So one has to use optical modeling there. The third one is a support structure. Support structure means everything is held on that. So support structure is it should withstand high wind loads. This thing. So it's a structural component. Structural means it's a mechanical structure, mechanical design analysis. So now you may need three different types of softwares. Is it clear? So for thermal analysis, generally CFD is used, computational fluid dynamics softwares, ANSYS or whatever you can see that can be done. Optical, there is several optical models, softwares are available. One of the optical software is ASAP, and then that is they're mainly based on the ray tracing approach. We can also, one can write your own code like a Monte Carlo ray tracing technique. By based on that, one can write own codes depending upon the, either it can be a MATLAB code or any other code. Then structural purpose, we can go for FEM analysis. We can go for that, and that is also again ANSYS. For CFD ANSYS Fluent, this is ANSYS structural FEM analysis. For optical, it's a ASAP. But again, once you have a system, then you have to do it thermodynamic analysis. Thermodynamic means how much energy is there and how it's converted into turbine and all this. There are two softwares mainly available. For 4E analysis, there is a software called Transys. This is TU Delft has developed that. The other one is this one. Sorry, Transys is used for thermal analysis. But for thermodynamic analysis is what we call that. The TU Delft is a 4E analysis based system software. It's called Cycle Tempo. That is a Cycle Tempo. This is Transys. So for thermodynamic and cycle analysis, you have a Transys and Cycle Tempo. For structural analysis, you have this one, FEM based this one, and fluid dynamics side, you have heat transfer and fluid dynamics, you have Fluent and optical ASAP. So these are the different softwares generally we use. Clear?
Thank you, sir. Thank you.
I have one more question. Can I ask, sir? But this is
Yes.
not. This is suppose in cooling tower there is huge evaporation loss is happening. So how to reduce that evaporation loss? Because this is not in this syllabus, but I hope.
Don't worry. You can ask any question related to energy generation. There's no problem. Okay, or power generation, or heat transfer, or you can ask any question. No problem. So how to avoid evaporation losses from cooling towers? For which cooling tower?
This is a centrifuge type cooling tower.
No.
And,
What is the purpose?
purpose is we are having a aluminum rolling mill complex here. I am from industry background. That's so I am present in Hindalco, Aditya Birla Group. So we are having a aluminum rolling mill here. That cooling tower, whatever the water is in for that heat
Oh.
exchangers. Heat exchanger inlet and outlet. So that cooling tower delta T as per designing it is 8 to 10 degree, and flow is 980 meter per hour, and the capacity is 3000 cubic meter.
Okay. See, in fact, I have designed with because you know that these power cooling towers are of small capacities, but we have even vetted and given some design project of a cooling tower whose height is about it's called natural draft cooling towers. So this so maybe you are using forced draft. There will be a fan which circulates that. That is a different. But generally, this big power plants, there is a hyperbolic big power cooling towers are there, and especially this cooling tower, what we designed was about 204 meters height. That is the highest, I think, in India. What happens is the cooling tower performance depends on the local conditions, which type of weather conditions it prevails. So especially when we set up a solar thermal power plant in Rajasthan, where the water is a problem, water is scarce. So in such case, because the evaporation losses are very high, and it can when in dry conditions, humid conditions it's okay, but dry conditions it's a very huge losses. So the one option is there is a proper design of drift eliminator. You have to come up with a drift eliminator, proper drift eliminator, proper fill, fill or packing. That's called packing. These two things, and of course, distribution system, water distribution system. So three things are important: the design of these three: distributor, drift eliminator, and packing. These three designs need to be done for reducing the evaporation losses. But if really water scarcity is there, then it's very difficult, because in Chennai we have a water problem. So we have to design an air conditioning system for our library. The water was the problem. Then what we did was we went for dry cooling tower. You can go for dry cooling tower where the air is only used as a coolant. So in such case, depending upon that, if you want to really minimize the drift elimination or the evaporation losses, we can go for these three designs. But if you want to replace that by another cooling tower, then you go for a dry cooling tower. But the problem with the dry cooling tower is the cost is relatively higher, but there's no water usage.
Thank you, sir. Thank you. Thank you.
Sir, I want to add one point on these cooling towers.
Okay, please go ahead.
Yeah, one of the element in poly generation, we have desalination system. Recently, one of the industry people, they approached the challenge and some solutions, especially for the losses, evaporation losses coming from the cooling towers. So there is a one desalination technology, water cycle, where air can be humidified and then followed by dehumidification, like condensation. If the people are applying, because already they have hot water, if they are applying this heating, humidification as well as dehumidification for a cooling tower, they can recover the water. They can recover the water, and same water they can use for the power plant, because any thermal power plant, any solar thermal power plant or conventional thermal power plant, they needs the a water plant, water purification plant. So this can be used as an input to the water purification plant. So that is not the waste. Then if they are adding that cycle, water cycle, that is not the waste. They can convert into the useful form.
I agree with you that yeah, but what he's I agree with you, but see, generally what happens is, see, condenser. What is the condenser? Condenser cooling tower can be eliminated completely when you go for water body. So you take water from a river or a sea and use it in condenser and reject back into that, then completely we can eliminate the cooling tower. And the another method is instead we don't have that water bodies. What we go for air cooling. That is a cooling tower. But then what you are saying is the base for condenser. If you want to add one more component, it's a cooling tower. But the cooling tower heat losses you want to water evaporation losses if you want to avoid, what that you are doing is after evaporation you want to condense it by adding another component. That is a cascaded component. So therefore it's again judicial mix of it's a worth going, but it's a judicial mix of cost and complexity.
So yes, sir.
Any more?
Hello.
Hello? Yeah.
Can you hear me?
Yes, sir. Who Krishna?
Sir, I just yeah. Sir, I got a doubt. That for a PCM thermal energy storage system, say we need to find out the amount of how much energy it's stored for a particular time. We know that there is two types of heating process happens: sensible heating and latent heating. So we need to find out how much amount of heat it absorbed as a latent heat and how much it absorbed as a sensible heat, and how we can find out this value, because sensible heat happen in two stages, in the solid state as well as in the liquid state. So if someone need to find out how much the sensible heat absorbed by the particular domain or a PCM storage device and how much it absorbed as latent heat, then how we can find these values? Because I see in a graph of yourself and see that this much is latent heat and this much is sensible heat, and how we can find these values?
What experimentally or by analytically?
Say using a software Fluent or any other the numerical technique.
Oh, it's a simple energy balance only. Simple energy balance is you know the temperature, melting temperature, you know, and boiling temperature, you know, isn't it? That when it converts into liquid. See, generally what happens is it converts from first solid to liquid. That is again you're talking about phase change. That's a phase change, isn't it? So,
Yes.
if it is solid to liquid is a phase change, and
Yes,
liquid, you are vice versa. After liquid, you can, if you want to raise the temperature, you can still raise till below boiling temperature, isn't it?
Yes, sir.
So then what you have to define what temperature you are going to raise, that sensible part. See here latent is a liquid, solid to liquid is a sensible, solid to liquid is a phase change, that is a latent heat.
Yes.
At that temperature, what is the mass and what is the temperature at which, what is the latent heat of fusion or evaporation? You can find out. That is that you can numerically or analytically you can do it by writing energy balance to that. Okay, based on the conditions. But experimentally, it's a different concept. I don't think you are interested in experimental.
I do also experimental study, sir. For a numerical study itself, say at the I'm heating it for 2 hours. At the first after 1 hour, we can see certain part of the fluid will be in liquid state and certain part in the solid state, and some zone will be in Michigan, or some zone will be there at the interface. Okay. So liquid phase, when you heat it up, the liquid sensibility will rise. I mean, say one side heating is happened.
I understood. This is called moving boundary problem.
Yes.
Because there is a solid liquid interaction. You understand? See, if you, for example, if you heat wax, okay, initially some part of wax is converted into liquid, and there will be a convection between the solid and liquid, and then that is further like ice. You know, if you put ice into water.
Yes.
How ice will disappear after some time. That is an important thing. So therefore, if you look at a solid portion and then start adding heat, what happens? It will become liquid. But there are two things. We have to also see that what is the liquid-solid boundary. Then how is it moving? It's a dynamic movement. With the temperature, completely the boundary moves. So therefore, your problem is the boundary problem. You understand? So that mesh shape boundary is important. So then, but that boundary is not fixed. You have to make it a moving kind of boundary.
Yes.
Then you will be able to find out the temperatures. But I don't know whether you must be fixing. And another thing is a buoyancy effect will be there in case of what is the study case, because the not only boundary moves but also it floats.
Yeah, the convection happen so that
convection happens and conduction within the solid region. So it's a complex, but I think you can offline we can discuss if based on your problem we can see that. But generally, it's if you consider moving boundary with the buoyancy effect, that will take care of that.
okay, sir.